Okay, so we're going to find all of our local maxes and mins. This is a polynomial. My domain is all real numbers. My domain is the unbounded interval negative infinity to infinity. We are not guaranteed to have global maxes and mins. And come on, we've all taken college algebra. We know that this graph, it's a cubic. It's going to look something like this. We know there's going to be no global max or min. It goes on up forever and it goes down forever. So he's not going to have a global max or min on negative infinity to infinity, but he will have a local max and he will have a local min. We're going to find those. Now, later on a separate day, we're going to learn the second derivative test to figure out algebraically using calculus whether a critical point is a local max or a local min. Today, we're going to figure these out using the graph. So we're just going to graph this guy and figure out whether we got ourselves a local max, local min, and so forth. Like I said, pretty soon we'll learn how to use the second derivative test to tell us what kind of max or min we have. All right, so we want to find the critical points. I'm going to give you guys a hint for the rest of the semester. Like, I'm not saying this always holds true, but if you're working on a calculus problem and you don't know what to do, like 85% of the time, the right answer from now on, from this moment on, is set the derivative equal to 0. Like, we're going to be doing that so much. Take the derivative, set it equal to 0. Find our critical point. So this guy's derivative would be, you should just be able to do this in your head, x squared minus 5x plus 4. So again, you should just be able to check that in your head. Critical points occur when the derivative equals 0 or is undefined. That's the one people forget to check. And how are you undefined? Usually some denominator equals 0. Like if you've got some rational function or some fraction, your derivative will be undefined when the bottom equals 0. That doesn't happen here. This guy's defined everywhere. That's also a polynomial. He's defined everywhere, so that's not going to happen in this case. That guy's always defined for all real numbers. The domain of the derivative is all real numbers. So my critical points will occur when the derivative equals 0. That's, oh, come on. We can just factor that. That's x minus 1, x minus 4 equals 0. We got two factors, set each one equal to 0. You get 1 and 4. So I have two critical points. I'm going to have one at x equals 1 and one at x equals 4. Now, again, we've all taken college algebra. We know this is a third degree polynomial. We know the end behavior is going to be right arm up, left arm down. Like, you should know that from college algebra and pre-calculus. I know my graph is going to shoot up like this and down here. I could figure out where all of his intercepts are. He's a third degree polynomial. He's going to have 3 roots, not necessarily distinct. We know that's going to happen. We know we're going to have possibly 3 x-intercepts. Like, we could go through all that work and figure out where the x-intercepts are. We know that the number of turning points is usually 1 less than the degree. We're probably going to have 2 turning points. So my graph is probably going to look something like this. Now, maybe this dip actually comes down 1 and 4. maybe it actually goes like this. And those will be my 3 intercepts. I don't care about that right now. What I'm trying to point out is just from our knowledge of graphing polynomials, we should be able to see that the max or the critical point at 1 is going to have to be a local max. And the one at 4 that I kind of missed here is going to have to be a local min. Like we should be able to just figure that out based on what you know from college algebra and pre-calculus. Next time when we get to curve sketching, we're going to show all that. We're going to use the second derivative test. We're going to find all the intercepts. We're going to draw a very detailed graph of this. For now, I'm just saying, hopefully you can just see that this is what we're going to get. Let's plug this into Wolf or Desmos and look at it. So that was y equals 1/3 x cubed. I think it was minus 5/2 x squared. Yeah. And then plus 4x plus 4x. Yeah, so there's what our graph actually looks like. So that guy right there at 1 is a local max. He's a high point. That guy right there is a local min. So that's local max. And that's a local min. Now, local max of what? Let's find our y values. So I have a local min at x equals 4. That's the location of what? Now, a lot of mistakes happen here. When I ask students, find me the local min, they'll take that value right there and they'll plug it in the derivative. I already know what happens when you plug it in the derivative. You get 0. My tangent line is horizontal right there. I already know, don't write this. I already know f prime of 4 equals 0. I just found that right there. Don't plug it in the derivative, plug it back in the original. I want the actual y value. So of f of 4, and I'm just gonna go here to the picture and see. It's negative, negative 2 2/3, so negative 8/3, I think that is. You can check my arithmetic there. I'm just using the picture. And we have a local max at, this is the x value, the location, x equals 1 of, and then I want the original y value. I'm using the function. I'm literally just plugging in 1 here. But again, I'm lazy. I don't feel like plugging it in. Okay, evidently we're going to have to plug it in, whatever that is. 1.8, I'm going to approximate it. Like it would be some fraction, 1.833, whatever that. Okay, let's look at this guy. Same idea. This is a 6-degree polynomial. I'm not going to go through all the trouble of multiplying all that out and getting some 6-degree polynomial. I'm going to use chain rule to find his derivative. So we find all of our critical points. Critical points happen when the derivative is undefined or the derivative equals 0. So let's take the derivative. I'm going to use chain rule here. That 3 is going to come down front. drop down to 2 times the derivative of what's inside. What's the derivative of what's inside? 2x. This is a polynomial. This guy's defined everywhere. The domain of the derivative, same as the domain of the original in this case, all real numbers. I don't have to worry about places where the derivative's undefined for this example. I want to know where does this equal 0. So let's set this equal to 0. I don't want to multiply all this out. The entire point, the reason we taught you factoring back in intermediate algebra is to use what's called the zero product. I'm going to write it down. The zero product property of equality. And that property says if two things multiply together to be 0, then one of those things must be 0. That's what I've got here. I got a bunch of things multiplied together to be 0. This is literally the reason we factor. This is why we teach you factoring. It's why you got to be an expert at factoring. So if you're trying to solve some polynomial equation, you want to use this product, zero product property. You want to get a 0 on one side and you want to factor and set each factor equal to 0. That's already done for me. I've got 5 things multiplied together. I've got 2 times an x squared minus 1 times another x squared minus 1 times a 2 times an x all equals 0. The only way that's possible is if either x squared minus 1 equals 0 or 2 never equals 0, x equals 0. This one says x squared equals 1, so x is plus or minus 1. And that one says x equals 0. So I have 3 critical points. Now I want to figure out which of those are local maxes, mins, or neither. Like we might have a spot where the graph may be at 1. Maybe it comes up like this. It looks like it's going to level off. Oh, but then it goes up like x cubed does. So maybe it kind of comes in horizontal for just an instant like that. We might have here at 1, the graph comes up and goes back down. We might have a local max. We might have the graph comes down like that, a local min. Again, pretty soon we're going to learn second derivative tests, which will tell us all of those. We just find this using calculus. But for now, we're just going to type this into a graphing calculator and figure out who's a local max, who's a local min. So my function was x squared minus 1 all cubed. And look at that. So these are critical points, places where the derivative equals 0. But that's neither a local max. It's not the highest point around. It's not higher than these guys. It's not a local min because it's not lower than these guys. It's what we call a saddle point. So he's neither, same with him. But that guy right there is a local min. He also happens to be the global min. We weren't guaranteed we'd have globals, but we do. That is both the local and global min at x equals 0 of -1. So we have a local, that's all we're asked about, local min at x equals 0 of y equals -1. We had 3 critical points. All the locals have to occur at critical points. Only one of them happened to be a local. Okay, let's do one more in this video. This one's going to be a little more challenging. Okay, let's take the derivative. So f prime of x will be quotient rule, derivative of the top times leave the bottom alone, minus derivative of the bottom times leave the top alone, all over the bottom squared. Okay, let's clean that up a little bit. See, before, when I had you using quotient rule, I always said, just leave it the way it is. Don't worry about cleaning it up. Now we have to. Because now we're going to do some math with this. We're going to have to do a little algebra. So what do we get? 4 plus 4x squared minus 8x squared all over 1 plus x squared squared. Okay, critical points happen where the derivative does not exist. Where does the derivative not exist? When the bottom equals 0. So where does 1 plus x squared squared equals 0? That would mean 1 plus x squared equals 0. That would mean x squared is -1. No real numbers work there. So there's no solution to that. So we don't have any places where the derivative for this particular example is undefined. In fact, the domain of this is all real numbers. What about where the derivative equals 0? Okay, this is a little shortcut for you. The only way a fraction can equal 0 is if the top equals 0. I would write that down in my notes. Fraction equals 0. The only way that's possible is if the top equals 0. So this is what we're always going to do when we get these weird fractions. Bottom equals 0 is where you're undefined. Top equals 0 is where the derivative equals 0. So you're always going to set both equal to 0. So let's clean that up a little bit. That was 4 minus 4x squared. So just combine like terms equals 0, or 4 equals 4x squared. That's x squared equals 1, which implies x is plus or minus 1. So we have two critical values here. Now we want to figure out who's a local max, who's a local min. Again, next time we're going to learn second derivative rule. We're going to learn increasing, decreasing. We're going to do curve sketching. For now, we'll just type that into some graphing program. Oops. 1 plus x squared. So it looks like I've got a local max at x equals 1 and a local min at x equals -1. Now, if we scan out, it looks like those are also global maxes and mins. Remember, if we're not on a closed bounded interval, we're not guaranteed to have globals, but we might still, and this one seems to have. Now, we haven't proven that. I don't know, maybe when we get way out here, this graph shoots back up again. It doesn't, but we haven't proven it doesn't yet. So maybe you're not convinced that that is the absolute maximum point. It is, but again, you might not believe that yet. So that guy is a local max, and he's a local min. And what's the actual y values? It looks like 2 and -2. So this original function has a local max of 2, that's the y value, at 1, that's the x value. And f has a local min of -2 at -1. The of is the y value, the at is the x value.